Welcome to the Deep Dive, your shortcut to being genuinely well-informed. We take a stack of expert sources, boil them down, and give you the insights you need.
Glad to be here.
Today, we're plunging into something absolutely foundational. Fundamental to every single building you've ever been in. But honestly, it's often overlooked.
It really is.
We're talking building science, specifically that outer skin of the building,
Yeah,
what the experts call the building envelope.
that's the one.
And this isn't about, fancy finishes or paint colors. This is serious business. We're calling it the battle for the building envelope.
A battle is a good way to put it.
It's this constant, relentless struggle against, well, the forces of nature, physics. Every single day, the skin of your house, your office, wherever, it's fighting this silent war.
To keep you safe, comfortable, dry. It's critical.
And it shapes everything, right? How long the building lasts, how comfortable it feels, how much energy it uses. It's huge.
Absolutely. It's the core job. Architects get the spotlight for how things look, the cool shapes and all that.
Right.
But the envelope, that's doing the primary work of shelter, keeping the inside in and the outside out. Comfort, durability, energy efficiency. It all hinges on the envelope.
So understanding this isn't just for builders then.
Not at all. Anyone who lives or works in a building, anyone who wants to understand how buildings actually perform needs to get a handle on this. It's a direct line to understanding real performance and maybe even well-being inside.
Okay, so for this deep dive, we've got some amazing guides, people who really know their stuff. We're leaning heavily on Joseph Listerberg. His Builder's Guide to Hot, Dry, and Mixed Dry Climates is basically like a Bible in this field.
A cornerstone, definitely. Very practical, very science-based.
And we've got Francis D.K. Ching's Building Construction Illustrated, visually brilliant stuff.
Yeah, Ching makes complex ideas really clear with his drawings. Invaluable.
Plus, we'll dip into some historical text, too, just for perspective. So get ready. It might sound dry, building science, but I promise you there are some surprising facts, some real aha moments coming.
For sure.
We're going to uncover why getting this envelope right is maybe the single most important thing for making buildings that last, feel good, and don't cost a fortune to run. Okay, let's unpack this. Let's start with the big one. The most obvious enemy, water. Rain control. Sounds simple, right? Keep the rain out.
Yeah.
Seems basic, but it's way more complicated than just, sticking a roof on top and some siding on the walls. What makes it so tricky?
Well, it's fascinating because modern thinking isn't just about creating some perfect impenetrable barrier. That's almost impossible long term.
Okay.
It's more like this sophisticated dance, a layered strategy. Joe Steiberek talks a lot about the rain screen approach.
Rain screen. Okay, what's that?
The basic idea is, yes, you have an outer layer, your siding, your brick, whatever, that sheds the bulk of the water, the driving rain.
Right, the first line of defense.
Exactly. And this is the key part, you assume some water will get past it. It always does, eventually.
Okay, so what then?
So behind that outer layer, you design in an air gap, a small space, a drainage plane. Any water that sneaks past the cladding hits this gap and can just drain down and out harmlessly at the bottom.
So it manages the water instead of just trying to block it.
Precisely. And just as important, that air gap allows air to circulate behind the cladding, which helps dry out the whole wall assembly. If any moisture does get absorbed, it promotes drying.
That makes so much sense.
Yeah. And this kind of robust strategy is absolutely essential, especially, as Esteberg says, for assemblies that are susceptible or vulnerable to moisture damage. Think wood framing, certain types of insulation. You can't just hope for the best. You have to plan for water getting in and plan for it getting out.
So it's not just stopping water, it's managing it. And that drying part sounds crucial too. If it gets wet, it needs to dry out. What affects how well a wall can actually do that?
Oh, that's a whole other layer of complexity. The drying characteristics, as the experts call it. It depends on a bunch of things interacting.
Like what?
Well, the materials themselves, obviously. Some hold moisture, some release it easily. Then the insulation, where it is, what type it is, can trap moisture or let it pass.
Okay.
Then there's the climate. Big difference between trying to dry a wall in, say, Arizona versus Florida, right?
Huge difference.
Yeah.
Humidity, wind.
Exactly. And finally, air movement through the wall assembly itself. Even tiny air currents can carry moisture in or out. So if you've got a wall design that doesn't dry easily in a damp climate, well, your rain control, that outer layer and drainage plane, needs to be absolutely bulletproof.
Wow. It really is an ecosystem, isn't it? Everything connected.
Totally.
I can see that balance playing out when you look at something like roofing. Ching's Building Construction Illustrated goes into such detail on different roofing materials.
Yes, he does.
And it's not just looks. Each one needs specific underlayments, specific pitches, minimum slopes.
Absolutely. That's physics in action. Ching makes it crystal clear. You can't just slap any shingle on any roof slope.
Right.
Like common asphalt shingles. Most need at least a 4 and 12 pitch. Any shallower, say down to 3 and 12, and you often need to double up the felt underlayment.
Because the water runs off slower. More chance to get in.
Exactly. Wood shakes. They're rougher. They might need a heavier 30-pound felt, sometimes interleaved between courses, depending on the pitch. Wood shingles have their own rules.
These aren't just suggestions, then. They're requirements based on how water behaves.
They are hard-won lessons. Ignoring them. You're basically asking for leaks. You're fighting gravity instead of using it. The battle's lost before you even start.
It's amazing how persistent water is.
Yeah.
And this kind of detailed understanding, it's not brand new, is it? People figured this stuff out a long time ago.
Oh, centuries ago. You look back at someone like Palladio, the Renaissance architect, writing in the 1500s.
Yeah.
He's talking about different kinds of lime mortar, how one type, made from a spongy sort of stone, is good for general plastering. But another type, from a scaly, rubbed stone, makes lime that's excellent for such buildings as are most exposed to the weather or stand underwater. Wow. Because, he says, it immediately sets, grows hard, and is very lasting. That's 16th century material science. They knew you needed the right stuff to fight the weather, especially water.
That's incredible. And when you bring organic materials into it, like wood, water isn't just a problem, it's the problem.
It absolutely is. Bruce Hoadley's book, Understanding Wood, has this staggering statistic. Something like more than 90% of all problems with wood involve moisture.
90%.
Yeah. It's not just rot, though that's part of it. It's stability. Wood swells and shrinks dramatically with moisture changes. That affects joints, finishes, everything.
Warping, checking.
Exactly. And its resistance to fungus, to decay, is hugely dependent on keeping it dry. Hoadley mentions that freshly cut pine sapwood can be over 200% moisture content.
Meaning more water than wood by weight.
Yeah. Twice as much water as wood. Managing that moisture, keeping it below critical levels in the finished building, it's absolutely paramount for wood to last. Ignore it, and failure is basically guaranteed.
Okay, let's shift gears. Air. Invisible. You can't always feel it. But it seems like air leaks are a huge deal in building performance. Why is a small, unseen air leak such a big problem? It's not like a drip, right?
No, it's much more insidious. Air leaks silently sabotage the whole system. Listerberg really hammers on the importance of air leakage testing, not just for the walls and roof, but for ductwork too.
Okay.
Because air doesn't just move because the wind blows. There's this thing called stack action or stack effect.
Stack effect.
Yeah, warm air inside a building is buoyant. It wants to rise. So in winter, it pushes out at the top of the building and creates negative pressure lower down, sucking cold air in through any little cracks or gaps.
Oh, like a chimney.
Exactly like a chimney effect. And mechanical systems, furnaces, air conditioners, exhaust fans, they move air around too, creating pressure differences. Leaky ductwork is a huge culprit.
So even a tiny gap can let a surprising amount of air through.
Absolutely. And that unwanted air carries moisture with it. It carries heat out in winter, heat in summer, dust, pollutants. It completely bypasses your insulation and messes up your indoor air quality. It's like death by 1,000 cuts for building performance.
So where are these leaks hiding? Not just the obvious crack around a window, I assume.
No, the sneaky ones are often where different systems meet. Hulsteberg points out ductwork penetrations where ducts go through walls or ceilings as critical spots that have to be sealed perfectly, airtight, and insulating.
Makes sense. Ducts carry conditioned air.
Right. But here's a really surprising one he highlights. The connection between the air handler unit itself, the furnace or AC unit, and the platform it sits on.
Really? Just where it sits?
Yeah. He says significant leaks happen there. All sides need to be sealed to the platform. And the big metal box connected to it, the supply plenum, notorious for leaking at the seams. His recommendation for those areas, because they vibrate and flex more, is to use both fabric and mastic, like a mesh tape embedded in a goopy sealant. That level of detail shows you how determined air is to find a way through.
It's funny, isn't it? We get really good at making buildings airtight to save energy, and then we create a new problem because nothing can get out. The ventilation paradox.
That's exactly it. It's a classic systems thinking problem. Allen and Thalen, in their book Fundamentals of Residential Construction, point this out clearly. We strive for these tighter envelopes, which is great for energy bills.
Right.
But then all the indoor stuff, moisture from cooking and showering, odors, chemicals off-gassing from carpets and furniture, just us breathing, it all gets trapped. It can build up to intolerable and often unhealthy levels.
So we save energy, but make the inside air potentially toxic. Not a great trade-off.
Not ideal, no. We essentially seal ourselves in with our own pollutants.
So what's the answer? You need fresh air, but you don't want to just open a window and dump all that conditioned air you paid to heat or cool.
This is where technology steps in. Allen and Thalen talk about heat recovery ventilators, or HRVs. You might also hear about ERVs, energy recovery ventilator.
HRVs, okay.
These are pretty clever devices. They constantly exhaust stale, polluted indoor air, but before they dump it outside, they pass it through a heat exchanger core.
Okay.
At the same time, they're bringing in fresh outside air, passing it through the other side of the heat exchanger. So in winter, the outgoing warm air preheats the incoming cold, fresh air.
It transfers the heat.
Exactly. It recovers maybe 70–80% of the heat from the exhaust air. In summer, it works in reverse, pre-cooling the hot incoming air.
So you get fresh air without the huge energy penalty.
Precisely. It addresses that dilemma. Tight envelope for efficiency, but managed ventilation for health. They're becoming pretty standard, almost essential in high-performance homes now.
And it's wild to think this whole issue of bad indoor air isn't new. You mentioned historical examples.
Yeah, it really isn't. If you go way back to Agricola's De Re Metallica from 1556, it's this incredible book about mining and metallurgy. Yeah, and he describes in detail the problems miners faced with air quality deep underground. He talks about stagnant air causing difficulty in breathing, simple lack of oxygen.
Okay.
But then he describes worse things. Air infected with poison from the minerals themselves, what we'd now call toxic fumes or gases. He talks about illnesses, even death, caused by this bad air in enclosed shafts and tunnels.
Wow, in the 1500s.
And he even describes early ventilating machines, bellows, fans, sometimes driven by water wheels trying to force fresh air into the mines. So this fundamental problem of making enclosed spaces breathable and healthy, people have been wrestling with it for centuries. The context changes, but the core challenge remains.
Okay, this next one. Vapor. This feels like the trickiest element. It's not liquid water. It's not moving air. It's this invisible gas that depends on climate. Why are vapor barriers or vapor retarders so critical in some places but actually harmful in others? This one really bends my brain.
It is tricky, you're right. There's no single answer that works everywhere. And it ties right back to those drying characteristics we talked about, and crucially, the interior and exterior climatic conditions. Liz Staburek digs into this deeply.
Okay.
So the main job of a vapor retarder, let's call it that, it slows vapor down rather than stops it completely, is to prevent water vapor, which is always in the air, from moving through your wall or roof assembly and hitting a cold surface where it condenses into liquid water.
Right, condensation inside the wall. Bad news.
Very bad news. That's called interstitial condensation, moisture inside the structure. It leads to mold, rot, ruins insulation, all the bad stuff.
So the vapor retarder stops the vapor before it hits that cold surface.
Ideally, yes.
Yeah.
Typically, in cold climates, you put the vapor retarder on the warm side of the insulation, usually just behind the drywall. It stops warm, moist indoor air from getting into the cold wall cavity.
Okay, makes sense for cold climates. But why is bad elsewhere?
Well, think about a hot, humid climate, like the Gulf Coast. The moisture drive is mostly from the outside trying to get in. If you put an impermeable vapor barrier on the inside behind the drywall like you would up north, yeah, moisture gets into the wall from the outside, hits that cool air-conditioned drywall, wants to dry inwards, but it hits that vapor barrier and gets trapped. Now you've created a moisture sandwich inside your wall.
So you actually caused the problem you were trying to prevent.
Exactly. That's why in hot, humid climates, you generally don't want an interior vapor barrier, or you want one that allows some drying inwards, a smart vapor retarder. It's all about understanding which way the vapor is trying to move and making sure the wall can dry out in at least one direction.
So it's not just about blocking vapor. It's about managing where condensation could happen.
Yeah.
And trying to prevent it within the wall itself.
That's the goal. One key strategy L. Steiber mentions is using rigid insulation on the outside of the wall sheathing, continuous exterior insulation.
Right, you see that a lot now. Foam boards on the outside.
Yeah. It does more than just add R value. By wrapping the outside, it keeps the structural sheathing warmer. It helps control condensing surface temperatures within the wall assembly. If the sheathing stays warm enough above the dew point, then water vapor moving outwards from inside won't condense on it.
Oh, so it changes the temperature profile inside the wall. Clever.
Very clever. It's managing the physics, essentially, allowing the wall to dry outwards while preventing that internal condensation surface.
Can you give a really practical, common example where getting vapor control wrong leads to big problems?
Sure. Listaburg gives a great one. Flooring over concrete slab-on-grade foundations, where the concrete floor is right on the ground.
Yeah, common in many areas.
He strongly advises against putting impermeable interior finishes, think sheet vinyl flooring, certain types of carpet backing directly on that concrete,
That's
unless you take very specific precautions. You need, first, concrete with a low water to cement ratio, which makes it much denser and less permeable. Second, you absolutely need a good polyethylene vapor barrier underneath the slab, properly installed. And third, you have to protect the slab edges from capillary water wicking up from the ground.
So multiple layers of defense against ground moisture.
Exactly. If you miss any of those steps, especially that poly under the slab, ground moisture vapor will slowly but surely migrate up through the concrete. If it then hits that impermeable vinyl flooring,
Trapped again.
cracked again, leads to mold underneath, flooring peeling up, musty smells, huge problems, all from invisible water vapor moving through concrete. It shows how critical vapor control is, even at the foundation level.
Okay, let's move to something we all feel directly. Heat. The envelope is like the building's thermostat, right? Keeping us comfortable, keeping energy bills down.
Wow.
How does it do that?
Fundamentally, through insulation. Ching and Winkle in Building Codes Illustrated talk about insulation providing thermal protection. That's its job.
Right.
Resist heat flow.
Slow it down.
Slow it way down. In winter, it keeps the heat you generate inside from escaping out. In summer, it slows down the sun's heat from getting in. This resistance, measured as R value, is crucial for thermal comfort.
Makes sense.
And by slowing that heat flow, it drastically reduces how hard your furnace or air conditioner has to work. That means lower energy consumption, lower bills, and a much smaller environmental footprint. Good insulation is the frontline defense in the battle against energy waste.
But it's not just about stuffing fiberglass in the walls, right? The building itself, how it's designed, how it faces the sun, that matters too.
Oh, absolutely. Ching, in Building Construction Illustrated, makes this point really well. He says that for things like active solar energy systems, solar panels, to work effectively, the building first needs to be thermally efficient and well insulated. You have to plug the leaks first.
Right. Don't try to fill a leaky bucket.
Exactly. And beyond that, passive solar design is huge. Careful consideration of siting, orientation, and window openings to maximize seasonal solar radiation.
Yeah.
You want the low winter sun coming in through south-facing windows to help heat the place.
Passive heating.
Yeah. And you want overhangs or shading to block the high summer sun, preventing overheating. It's using the building's form and position to work with the sun's energy, not fight it.
Are there more advanced ways buildings are controlling heat now? Beyond insulation and orientation?
Definitely. Things are getting more sophisticated. Ching describes systems like double-skin facades.
Double skin, like 2 layers of glass.
Essentially, yes. 2 glazed layers separated by an air cavity, often several inches or even feet wide. This cavity can be ventilated.
What's the advantage?
Several. They offer great acoustic benefits, buffering noise, but the big thing is thermal control and ventilation. You can have independently operable openings in both inner and outer layers.
So you can control airflow through the cavity.
Right. In winter, you might keep it sealed as an extra insulating buffer, maybe even preheat ventilation air in the cavity. In summer, you can vent it aggressively to flush out solar heat gain before it reaches the inner layer. It allows for really dynamic, responsive control of heat and airflow.
But even simple things like skylights.
Yeah.
Putting a window in the roof seems like asking for trouble with heat, right?
It definitely poses challenges. Skylights are great for daylight, no doubt. But Ching points out you need careful consideration to the control of brightness and glare. Direct overhead sun can be intense.
Yeah, blinding sometimes.
And the big one is excessive heat gain in summer. A skylight can act like a magnifying glass, dumping huge amounts of solar heat into the space below. Often you need blinds or external shading devices to make them workable, especially in warmer climates. It's that constant trade-off, light versus heat control.
It's fascinating how much our expectations of comfort have changed. Things we just take for granted now were unbelievable luxuries not that long ago.
Stuart Brand captures this so well in How Buildings Learn. He talks about how grand hotels in the mid-19th century pioneered things like central heating.
Right. Before that, fireplaces, stoves.
Pretty much. People experienced that consistent warmth in a hotel, and then, Brand says, they took insistence on such luxuries home with them. Demand grew.
And air conditioning.
Same story. Brand points to air conditioning in movie theaters in the 1930s. People escaped the summer heat in these cool, dark theaters, and suddenly, living without AC at home seemed unbearable. These evolving expectations constantly pushed the performance demands on the building envelope. More comfort, more control, more energy use. It's a cycle.
Okay, let's zoom in on the wall itself. You mentioned these 4 critical layers needed for a high-performance wall to handle water, air, vapor, and heat. Could you break those down?
Sure. Conceptually, you need these 4 layers, and crucially, they need to be in the right place relative to each other. First, the weather-resistive barrier, WRB. Its main job is water control, stop the rain, drain what gets past. Think building paper, house wrap.
Okay, water control, layer 1.
Second, the air barrier. Its job is to stop uncontrolled air leakage, both inwards and outwards. This can sometimes be the same material as the WRB, like some house wraps, or it could be interior drywall or exterior sheathing with taped seams. Needs to be continuous.
Air control, layer 2. Continuous is key.
Third, the vapor retarder. We talked about this controls the movement of water vapor to prevent condensation inside the wall. Its permeability and location depend entirely on the climate. Could be polyethylene sheeting, could be smart vapor retarders, could even be a layer of paint.
Vapor control, layer 3. Climate dependent.
And fourth, thermal insulation. Resists heat flow, keeps heat in or out. Fiberglass, mineral wool, foam boards, cellulose, whatever provides the R value.
Heat control, layer 4. Got it. Water, air, vapor, heat. And you said the order is critical.
Absolutely critical. Get them in the wrong order, like putting the vapor barrier on the wrong side for your climate, and you can trap moisture, negate the insulation, cause all sorts of problems. The science is in the sequencing.
Can you give an example, maybe something a bit unusual, that shows these layers in action?
Yeah, Elsterberg actually details a straw bale above grade wall. Definitely unconventional, but it illustrates the layers perfectly.
Straw bale walls.
Okay. For water control, he shows hashtag 30 felt building paper, drainage plane draped over every course of bales, that's the WRB, shedding bulk water.
Right.
Then you have plasters on the inside and outside. These are critical. They act as the air barriers, and they also manage vapor diffusion into and out of the bales. Straw needs to breathe, so the plaster permeability is key.
So the plaster does double-duty air and vapor control.
Yes. And the straw bales themselves, that's your insulation. Massive R value. But because straw is organic and hates being wet, those WRB, air, and vapor layers have to be perfect to protect it. It really highlights how each layer depends on the others.
And sometimes a layer can do even more, right? Like adding fire resistance.
Yeah, exactly. Good design finds those synergies. Ching mentions in Building Construction Illustrated how coatings of Portland cement or gypsum plaster over masonry walls can significantly increase their fire ratings.
So the plaster adds fire resistance on top of finish, air control, maybe vapor control.
Right. You get multiple benefits from one layer if you choose and apply it correctly. It's about making every component work hard.
This sounds incredibly complex to get right in the real world, making sure all these layers are continuous in the right order, properly connected. How do designers and builders actually pull this off? Seems like a huge coordination nightmare.
It is a huge challenge, and it really points to the need for more integrated approaches. The BIM handbook makes this point strongly. Integrated design build firms, the ones that handle both design and construction or have very tight collaboration, will benefit the most.
Because the builders understand the design challenges, and the designers understand the construction realities.
Exactly. You need that construction knowledge feeding back into the design process early, not just handing off drawings and hoping for the best. Breaking down those traditional silos is key.
And technology must be a massive help here. BIM, building information modeling, sounds like it's made for this kind of complex coordination.
Absolutely essential. BIM isn't just 3D drawing, it's creating an intelligent model. It allows for construction-level modeling with details, specs, costs, all linked together. It's the base strength, as the handbook says, for collaboration.
So everyone's working off the same page.
Ideally, yes. Architects, engineers, contractors, subs, they can all access and contribute to this shared digital model. It helps visualize how everything fits together, especially those 3D interfaces.
But even with BIM, those interfaces, where different systems meet, roof to wall, wall to window, those must still be really tough to get perfect.
They remain the biggest challenge. The BIM handbook calls them out specifically. Many details describe the interfaces between different systems, roofing system to walls, doors, and windows, translations between material types on facades.
Why are they so hard?
Because you're joining different materials, often installed by different trades with different tolerances, different movement characteristics. Water, air, vapor, and thermal control layers all have to transition seamlessly across that joint. It's incredibly complex to detail correctly and even harder to build perfectly on site. Their definition, as the book says, is inherently difficult. These interfaces are where envelopes most often fail if they're not given obsessive attention.
Okay, so let's talk about those failures. Where are the weak links? Starting at the bottom, foundations, where the building meets the ground. How does the battle often start or get lost? Right there.
The foundation is critical. Fundamentals of building construction reminds us that footings spread the load and create a level base. But it's also ground zero for moisture intrusion. The ground is almost always holding moisture.
Right, water in the soils.
And concrete, while strong, is porous. That moisture is constantly trying to get in, either as liquid or vapor.
And it can wick upwards, like a sponge.
Exactly. That's capillary action. Lusteberg really emphasizes protecting slab edges from capillary water in slab-on-grade construction. If the edge of your concrete slab is sitting in damp soil, water will wick right up into it, bypassing any vapor barrier under the main slab area. It's a major, often overlooked entry point.
Can you give a real-world example? A common way this goes wrong?
Sulzberg talks about slab moisture problems caused by something really simple: irrigated plantings surrounding the house.
Watering the garden beds too close.
Yeah. You keep the soil right next to the foundation, constantly damp with sprinklers or drip irrigation. That saturated ground feeds moisture directly into the slab edge or even wicks up the foundation wall itself. Then it gets inside, causing mold behind finish boards, ruining carpets, making the house feel damp. All from watering the flowers too much, too close.
Wow. An unintended consequence. It reminds me, even historical engineers thought hard about this ground interface, didn't they?
They really did. Think about Isambard Kingdom Brunel, the 19th century genius engineer.
Built ships, bridges.
Yeah. Right. And when he designed the launching ways for his giant ships, like the Great Eastern, Rolt's biography notes he deliberately built in a limited resilience. The foundation wasn't perfectly rigid.
Why not? Seems counterintuitive.
His thinking was that a little bit of give would help ensure an even distribution of the weight of the massive ship as it slid down. It would prevent unequal settlement that could damage the ship's hull. It shows this deep understanding that the interface with the ground needs careful thought about managing forces and potential movement. Sometimes flexibility is stronger.
Okay, moving up from the ground. The roof. The umbrella, the first defense. But where it meets the walls, that seems like another really complex, high-risk area.
Hugely complex. The roof itself has layers, underlayments, shingles, or tiles, and as Ching details, the right type depends critically on the roof pitch, the slope. 15-pound felt, 30-pound felt. It all matters for shedding water effectively. A low slope needs much more care than a steep one.
So the basic shape of the roof impacts everything.
Absolutely. Kidder Parker's handbook notes that the type of roof chosen for design reasons directly affects how you handle hip and valley lines for drainage. Form has to respect water flow.
And connecting that whole roof assembly to the wall assembly below.
That's the tricky part again. Eastman singles out interfaces between roofing system to walls as among the hardest to detail correctly. You've got different angles, different materials, potentially high wind pressures, ice damming issues, and cold climates. It's a convergence zone for problems, if not done right.
And then there are the holes we punch through the envelope on purpose. Windows and doors. Necessary, obviously, but they feel like built-in vulnerabilities.
They are. Necessary penetrations, but inherently complex. Fundamentals of building construction breaks down a typical window opening. You've got the frame, the sill, the vision glass itself, trim pieces, maybe spandrel panel below. Each part, each joint is a potential leak path for air and water, and that's before you even get into flashing details.
Flashing is key around windows, right?
Absolutely critical. Proper flashing integrates the window unit into the wall's water and air control layers. Mess up the flashing sequence and you guarantee leaks.
And windows have other jobs too, like fire safety sometimes.
Yes, that adds another layer. Building Codes Illustrated points out that openings in exterior walls sometimes need fire-rated assemblies, like approved 34-hour minimum fire-rated protectives, depending on proximity to property lines or other buildings. So the window might need to resist fire spread as well as weather.
The windows are getting smarter too, aren't they? Doing more than just letting light in.
Yeah, technology is advancing there too. Xing mentions options like exterior layer of safety or laminated glazing, operable panels for ventilation integrated into curtain walls, even energy-generating photovoltaic technologies built right into the glazing. Windows are becoming more active components of the envelope system.
Okay, one more set of weak links.
Ah,
All the other penetrations. Pipes, vents, electrical conduits, and especially ductwork.
yes, don't forget those. Listaburek constantly reminds us about sealing ductwork through building enclosures and ensuring airtight connections at air handlers. These hidden pathways can allow huge amounts of air leakage, totally bypassing the insulation and compromising the whole system.
And codes recognize this.
They do. Building Codes Illustrated states that ducts, louvers, and similar air transfer openings must comply with detailed requirements. They aren't optional details, they are regulated because their impact on performance and even fire safety is significant. Every penetration needs careful sealing and integration into the barrier layers.
So when this battle is lost, when the envelope fails, what are the consequences for the people inside? We hear terms like sick building syndrome. What does that really mean?
It means the building itself is making people ill. Stuart Brand discusses sick building syndrome as a real, recognized issue. Occupants experience symptoms, headaches, fatigue, respiratory problems, allergies that get worse when they're in the building and better when they leave. But there's no single identifiable cause.
And this relates back to the envelope failures.
Directly. Especially that ventilation paradox we talked about. An envelope that's too tight without planned, adequate ventilation becomes a trap.
Trapping pollutants.
Exactly. Allen and Thallen describe how indoor moisture, odors, and chemical pollutants build up. Listiburek connects this trapped moisture directly to mold growth. Mold releases spores, VOCs. These are known health hazards. The very air inside becomes unhealthy because the envelope isn't managing moisture and air exchange properly.
It's that echo of the ancient miners again, isn't it? Trapped in bad air.
It really is. Agricola's miners suffering from infected air and poison from minerals in confined spaces. It's the same fundamental problem. Enclosed environments becoming unhealthy. Even early modern architecture, like Banna mentions with Neutra's Health House, was consciously trying to design for health, for light and air, recognizing this connection between building design and occupant well-being.
Beyond health, what are the tangible costs? The impact on the building itself and the energy bills.
Huge impacts. First, energy. Uncontrolled air leaks and moisture absolutely compromise insulation. Wet insulation doesn't insulate well, it's R-value tanks. Air leaking around or through insulation makes it useless. So your heating and cooling systems have to run constantly trying to compensate. Energy bills go through the roof.
Wasted energy, wasted money.
Totally. And then there's durability. Moisture is the enemy of most building materials. Agricola wrote about furnace powder cracking if damp or frozen. Hoadley details how wood warps, cracks, and rots due to its abnormal shrinkage properties and low fungal resistance when wet. Moisture degrades steel, corrodes fasteners, causes paint to peel, concrete to spall.
It just eats the building away.
Pretty much. Envelope failures kick off the cycle. Moisture gets in, damages materials, compromises insulation, increases energy use, leads to more occupant discomfort and health issues, requires costly repairs. It all links back to that initial failure to control water, air, vapor, or heat at the building skin.
Okay, this has been sobering. So how do we win this battle? How do we consistently build better envelopes? It sounds like it starts with really understanding the science.
That's the absolute foundation. Mastering building science, understanding how heat, air, and moisture move, that's the core message. It's the single most important best practice, as we've been saying.
And how do we ensure that science translates into reality on site?
Processes like building commissioning, CX, are becoming vital. The CMAA standards describe this as testing and fine-tuning systems, especially HVAC, during startup to assure proper functioning and adherence to design criteria. Good commissioning implicitly tests the envelope. If the HVAC system performs as designed, the envelope is likely doing its job reasonably well.
It's quality control, essentially.
A very sophisticated form of quality assurance, yes. Making sure the building actually works as intended.
This feels like a call for a shift in focus, maybe even in education. Getting back to the fundamentals of how buildings work, not just how they look.
There's definitely an argument for that. Viollet-le-Duc, back in the 19th century, critiqued architectural education for focusing too much on historical forms while ignoring practicalities like costs, the locality, the materials, or the local modes of building. There's always been this tension. We need designers who deeply understand the physics and the craft.
And technology and collaboration must be key to implementing this science today.
Indispensable. We talked about BIM. CMAA highlights how it enables design assessment and clash detection, finding problems like pipes hitting ducts before they happen on site. This prevents errors, especially at those complex envelope interfaces.
Saving time and money.
Big time. It also ties into things like value engineering studies, again from CMAA. These studies look at the whole picture: capital, operating, and maintenance costs. A better envelope might cost a bit more upfront, but the savings in energy and maintenance over the building's life make it a smarter investment.
So it aligns with long-term value.
And with sustainability goals, like LEED requirements. You can't achieve high levels of sustainability without a high-performance envelope. It's central to green building.
So ultimately, winning this battle against nature and physics, how do we keep learning and improving?
It comes down to learning from experience, honestly. Stuart Brand has that great line, "All buildings have problems, but only some correct the problems." We need systematic failure analysis. We need to study what goes wrong and why across the whole life of buildings.
Feedback loops.
Exactly. And Brand shares that quote from the old carpenter. "I do things better now because I've spent so much time fixing the things that I did when I was younger." There's no substitute for learning from mistakes, your own and others.
It also feels like a systems problem, doesn't it? The building interacting constantly with its environment.
Very much so. Donella Meadows' work on systems thinking is relevant here. She talks about the limits to growth archetype. Any physical system runs into constraints. The building envelope is constantly pushing against the constraints imposed by physics and climate. Smart design acknowledges and works within those limits.
But we're not just passive victims of physics, right? We have choices.
Absolutely. Samuel Florman, the engineer-author, made that point beautifully. Technology is not an independent force. It's an activity in which people engage because they choose to do so. We choose how to design and build. We choose whether to prioritize envelope performance, whether to invest in the science and the craft. We have the agency to win this battle if we decide it's important enough.
What an incredible journey through the science of shelter. It's clear the building envelope is this unsung hero, this complex, essential system working constantly to keep us safe, comfortable, and efficient. A building really is only as good as its skin, its ability to handle that relentless battle with the elements.
It truly is. And maybe a final thought to leave with. Viollet-le-Duc praised ancient Roman architecture for its judicious employment of materials and sound reasoning. Centuries ago, they understood the importance of fundamentals. So the question for us today is, how do we balance our modern aesthetic goals, our new materials, our changing climate, with that same level of sound reasoning about the building envelope? What will future generations think of our buildings if we fail to prioritize this fundamental battle? Will they see thoughtful design or just, as Rainer Banham might have put it, the embalmed result of style over substance? Something to consider.
A powerful question indeed. Thank you for that perspective, and thank you, our listeners, for joining us on this deep dive. Hopefully, the next time you look at any building, you'll see its envelope with new eyes, appreciating that silent, crucial battle it's waging every single moment. We'll see you next time on The Deep Dive.